said, what happened there? Oh, sorry, I thought my computer was doing something weird. Anyway,
okay.
I think we're okay.
Excellent.
Yes, hello, my name is Stephen Haddad. I'm a scientific software engineer in the informatics lab at the Met Office, which is one of the partners in the Impact Lab that's organizing today's event. And today's tutorial is the first of a two-part series on Introduction to Python for Data Analysis. So just a few words about the informatics lab. So we're a multidisciplinary team combining science, technology, and design. So we've done a lot of work with data science in a variety of ways. And so some of this talk comes from our experience with that and our work with our internal community of practice around data science at the Met Office. And the informatics lab is part of the Impact Lab, which is based in Exeter, in Southwest England, helping small businesses understand and exploit data science and environmental data for their businesses. So first of all, some introduction to some aspects of what we'll be covering over the next two sessions. So before I start on the slides, just to say that we did some events around data science over the summer. And we found that there was some interest in not just kind of thinking about the concepts around data science and machine learning, but in really getting down to the nitty-gritty details of how do I actually do this in Python, specifically for people who have some programming experience, but not experience in Python and the surrounding libraries. So to really make it practical for that. So in this session, we're going to look at introducing Python, but particularly for data science, data analytics, and give you some details of the language and why it's good. So we'll start by introducing Python, the language. So some of you may be quite familiar with Python. Others you less so. So it's a language that's been around a little while now, although I still think of it as a new language. It was created in sort of early 90s by someone called Guido van Rossum as a scripting language based on a previous one that he'd worked on. So he wanted to kind of correct all the flaws in a previous scripting language. So it's an interpreted language. That means that unlike a lot of the programs on your computer, you don't compile it and then run it. As you run the code, it gets interpreted as you go along. In terms of kind of programming details, it's what's called a dynamically typed language. So the objects in your language don't have specific types like strings or integers in the same way that you do in other languages. The whole type thing is much more flexible. From the point of view of the programmer, what's quite nice about it is that it has a multi-paradigm batteries included philosophy about it. And what that means is you don't have the core language, but in order to actually do anything, you have to install lots of third-party libraries that are very complicated to install. There's a lot of functionality that just comes right away with Python. It's easy to get started. And there's a large active user and development community supporting it with many different libraries, both very general purpose libraries, like the ones we'll be looking at over the next two sessions, but also a lot of domain-specific libraries for specific areas of business and web design and science and technology, supporting sort of more niche requirements. So that's Python. Just a brief intro. A brief intro then to data science. So I'm guessing some people have some knowledge of data science but are interested in kind of how to really do it. But just to give a broad overview, it's an interdisciplinary area of study, quite a new one that's perhaps still emerging, combining statistics and statistical modeling with computer science and information science, as well as various other aspects of science and technology. So it brings together many fields. It's quite a new paradigm within science and analysis. So you have sort of empirical science, which is all about taking measurements and observing the world. Then you build on that with theoretical science, that's putting together equations that describe things. Computational science, which is essentially doing simulations based on your equations to understand more about the phenomena you're studying. And then data science, which is really exploiting vast numbers of measurements, really, data, to gain greater understanding and maybe do predictions. So one of the common questions about data science is how is it different, for example, to statistics or data analytics? And to a certain extent, it's the same. There's statistics is a part of data science, as is data analytics, but there's more to it. And we'll see some of those tasks as we go along. You might think maybe why is it kind of its own thing? Why is it a separate field? And part of it is just that the challenges of data volumes that we deal with today are such that there's a whole set of skills, so many skills, that it's a bit much to ask for somebody to just kind of learn them on the side. It becomes its own speciality to have data scientists supporting people doing other work, doing business analysis or scientific analysis or whatever else their focus is. They can't do all the data stuff they need to because of all of the increasing requirements and demands of doing that. So there are many tasks involved in that. So for example, how to store the data and access the data efficiently, cleaning the data so it's usable, then analyzing the data to see some statistics about it, mining the data to really gain some insights, as well as visualizing the data in an intuitive way to be able to really get to grips with what it's telling you. So that's data science. So I guess for this workshop, our aim then is to say, well, why do we want to learn Python for data analysis? Why is Python a good tool to use for getting started with data analysis? Well, one of the reasons is just that there are lots of tools, lots of functionality and libraries and so on in Python that support this. So you don't have to do very much yourself. With only very few lines of code that are fairly easy to write, you can do some pretty sophisticated analysis. And at the same time, in spite of being quite powerful, it's quite easy to get started. That batteries included philosophy means you can install a few libraries pretty easily, and you can get started very quickly. It's quite portable. So Python these days runs on almost any computing platform you can imagine, from your own desktop or laptop to most commercial systems and servers, to increasingly popular, especially for data science, various cloud platforms. All the cloud platforms have extensive Python support, not just for core Python, but all the most important data science Python libraries as well. And that active community is important. So there's all sorts of websites and tutorials available online, reference materials, places you can ask questions and get support, just freely available from the community. And the last really important reason why Python is good is it's very good at interoperability. So you can interact with lots of different other systems, load lots of different data from different sources. And this is really important because the core of getting value from data analysis is not just loading one data set, but bringing together several data sets, combining them, and gaining new insight from that comparison. And Python is very good at being able to bring together different systems, different sources of data very easily. So now we're going to go on to the gist of the material. So we've got two sessions in this workshop. The first session, we're going to go through sort of the basics of Python and the sort of language features that are useful for handling data, processing data, and visualizing data. So I'll just on quite basic data as an introduction. That's today. And in the next session, then we're going to look at some more real world data from the climate and weather domains, since I'm from the Met Office, and understand how what the concept of data models is about, and how essentially data models will make all the stuff we've been talking about in the first session much easier and more intuitive, and enable you to do it on much bigger, more complicated data sets. So that will be in 2 weeks' time on the 8th of December. And we'll be doing all that through Jupyter notebooks, which I'll be showing you in a moment. And just to mention that we'll send out these links afterwards, but these notebooks that I'm about to go through are all free and available through GitHub, so you can go through it in your own time and run it on your own computers or wherever you want to run it at your leisure. So we will distribute these links, and also to say that these courses this course is kind of inspired by some of the existing courses that are out there. This one just sort of gives you, what I'll be going through just kind of gives you a flavor for it, introduction. If you want to go through much more comprehensive tutorials, I can recommend the software carpentry or data camp courses as being fantastic introductions to Python for data science. So before I can go on to the notebooks, are there any questions at this time?
I can't see anything, Stephen, but yeah, it's fine to continue.
Find my notebooks, which have gone away somewhere. There's the study wine. Apologies for the delay. Where did... in that window. So let's get started with the first part. So can people, if you have any problems, if you would like me to make the text bigger on the screen or anything, just let me know and I can do so. Just post something in the chat and we can adjust. But I'll assume everyone can see it okay at this stage.
Oh, we've had a request to ask if the text could be a bit bigger, please, Stephen.
Excellent. Is that a bit better, RG?
RG, can you see that now? Yes, brilliant. Thanks, Stephen.
Excellent, no problem. So we've talked a little bit about Python so far. As I said, there's a lot of excellent resources. There's those links again to some additional courses you can go through. And so in this session, we're going to go through some of the basic constructs of the language and why they're good for data science. So I said it's an interpreted language. That means you can run your code interactively. So from a command line or a terminal, rather than having to build your code and then run it. And your code runs in an interpreted environment, which is then interprets it to whatever the machine you're running on. Because ultimately, your code has to be interpreted to run on the particular processor hardware that you have, and the interpreter is what does that. But what it does mean is that your Python code can run on many different environments, so long as an interpreter, spelling mistake, an interpreter is available. So that's what it means to be an interpreted language, and one of the things that makes Python very useful on a variety of platforms. Another key concept I just thought I'd mention for those of you who are familiar with other programming languages is the concept of white space. So that's the spaces that indent or lines of code, which we'll see in a moment. They are important in Python. This is one of the things that people either love or hate about Python. And divide your code into blocks of code in various ways. So rather than having something like a semicolon specify where the end of a line is or the end of a function, white space is important. I just thought I'd mention that because you might otherwise look at the code and think it looks a bit weird if you're not familiar with that. So I think the easiest way to demonstrate that, though, is just take a look at some basic statements. And so, for example, here are some basic statements assigning variables in Python. And that's sort of general syntax, looks very familiar to anyone, I think, who's done some programming before, assigning a 3 to a variable, doing some maths and calculating it. I'll just thought I'd, at this stage, I'll just mention how I'm doing this for those of you who aren't familiar with Jupyter Notebooks. I'm doing all these through Jupyter Notebooks, which are themselves a very valuable tool for data analysis and data science. So I just thought I'd mention there's a variety of ways in which you can run Python. You can either run Python in a sort of more traditional way on the command line. So for example, just bring back that window. You can type Python in the command line, and then you get an interactive session. Let me show you how that works. Oh, I don't know if I can make that bigger. So, for example, type Python in the command line, and you get an interactive session, which you can run like so. And this is perhaps the sort of more traditional way to run Python. But in this case, we were using Jupyter Notebooks, which is a very useful tool where you combine your code, which is doing the data analysis or plotting a graph, something like that, combine it with the results of that code, as well as some description around the code. So you can do some analysis and then some code that does analysis and then explain what's going on in that code and what the results mean, all in a single document. So that's what Jupyter Notebooks are. And you'll see that it's divided up into cells like this. So you execute each of them one at a time. And then you see the results below the cell, for example. So if I run that cell and then that cell one at a time, and you see that if there's something to print out, then it will display below there, which could be a graph or anything. And so this is a very useful tool I just thought I'd mention because it's very widely used. In fact, a lot of big companies, for example, Netflix, have now adopted Jupyter Notebooks as their sort of go-to tool for sharing their results and doing data science within their organization, because it's a very nice intuitive way to communicate results and share results in a group of people, and who can then also rerun your analysis and make their own changes. So it's a very nice tool. So just thought I'd mention that for those who haven't come across them before. So back to how Python works. So some other kind of standard elements of a language. So you've got some numbers, you can do calculations. Handling strings is a very common thing you need to do. And so you can see, oh, actually, let me just clear my notebook. So let's run our code. And so you can see there we've done some maths calculations, and we've done a test of a Boolean expression and gotten the result. So that's all pretty standard programming type stuff. Strings are also fairly intuitive. So for example, here's a string, I'm printing out a string, there's the result. There's some quite nifty features with Python. Just something I should add at this point, for those of you who might have used Python before, but maybe not for a while, Python, the standard version of Python now is Python 3, Python 3.8 to be precise, which has some differences to Python 2, particularly around string handling. So you might look at this if you've used Python before and think this looks a bit different. That's probably the reason why. And yes, so one of the useful things is formatting, because often in data science, you're wanting to write some text about a result and then insert the result into your text kind of dynamically, and the format command is useful for that. And so we see here, if you have a string and you have an expression in these curly brackets, and then you use the format command, you can assign some value. So for example, we've calculated A times B up here. You can insert that into your string and print it out somewhere, or output it to a file, or record your result in some way, as you often will want to do in data science. So you can see there's two ways of doing it. You can either do it with the format command explicitly, or you can do the same thing using this format string shortcut, where you have put an F in front of the string, and then you can insert particular variables like A times B that we've created into your string. So that's fairly standard programming stuff. Should be familiar to someone who has used other programming languages. For somebody who's then new to Python, though, some of the core constructs of any programming languages are conditional statements, repetition, and functions, reusing of code. So a conditional statement is just where we say, based on some value, I want to do this thing, or if it's a different value, I want to do some other thing. So these are if-else statements. This is traditionally how they're implemented. And so, for example, here we're saying if A times B is greater than some threshold, do an operation. If it's less than that threshold, less than or equal to, then do some other operation. And so we can see here our threshold was set to 5, A times B is 6, so we expect it will do this operation, and that's what happens. So that's a conditional statement. fairly standard. That's just to familiarize with the syntax. You can see here how we're using white space to indent the things that the statements that are part of the conditional statement. And that's about all to say about syntax for now. So that's a conditional statement. The second language construct that's vital is repetition. So that repetition is just saying, I have a collection of things. I want to do something for each of the things in that collection, or do something on each of the things in that collection. And so in Python, that's traditionally implemented with the for loop, as in many other languages. And you can say, for each of the things in my collection, then do a function. And so you see that there. Range 5 just creates a collection of the numbers from 0 to 4 and then prints it out. So we've done that. Just for completeness, I should mention there's another sort of loop called a while loop, but that tends to be less important these days. That's a sort of from a more perhaps old-fashioned style of programming that's less appropriate to the sort of tools we'll be using for data science. And the last thing is reusing functions. So often you write code that needs to be used in lots of areas, and you don't want to manually rewrite that code, or even worse, copy and paste the code every time. You want to put it in a function which can be called repeatedly from other parts. And so you land up reusing the code and arranging things in nice logical blocks that make some sort of intuitive sense. So for example, if for some reason we were working with triangles, we might be interested in calculating the perimeter of the triangle as well as the area of the triangle. So we've written a function here to calculate the perimeter of the triangle, which is pretty simple if you have the length of the 3 sides. And then a slightly more complicated function which calculates the area using something called Heron's formula, which can calculate the area of a triangle from the length of the 3 sides. And that reuses our perimeter calculation. And so we're efficiently breaking up our code and reusing it rather than rewriting it every time we want to do it. And so you can see over here, now we call our function for perimeter, it gives us a result. Oh, hold up, I'll define my function. So you have to, in Jupyter, execute your code to define those functions, and then you can actually call them. So there you are, 3, 4, 5, 3 plus 4 plus 5 is 12. Looks like we've got the right result there. And similarly, the area of the triangles, this is, you might recognize this is a nice right angled triangle. So the area should be half base of perpendicular height, 3, 4, 5, 2 times 3, which is 6, and it is, yes. So that demonstrates how we've managed to create a block of code that we can call again and again. And so, for example, if I wanted to calculate the area of other triangles, I can do that as easily. And reuse that code. So those are the core constructs in any language. And essentially, we'll be building on that for the rest of the workshop, but to a certain extent I also mention these because these are the kind of low-level constructs, and hopefully as we build up the range of tools that we use in libraries, we'll essentially be moving away from manually processing all the data to making use of higher level constructs which kind of abstract away those details so we can focus on the problem at hand and not the details of how to compute the results. Hopefully the libraries take care of that for us. So let's go straight on to that and handling data in Python, but perhaps should pause, see if anyone has any questions about what we've talked about so far. Don't see any questions in the chat. Do feel free to add questions there and I'll respond to them when I can. No, I think we're okay. Yeah, so just do enter questions whenever you have them. And we'll move straight on to handling data in Python. So as I said, there is a lot of functionality included straight out the box with Python without installing third-party libraries. So we're going to start by looking at sort of native ways that Python handles data before we look at some extensions from third-party libraries and how they handle data perhaps slightly differently. And so the perhaps the core structure for containing data in Python is a list. And here we see how you create a list in Python. You use the square brackets and include some elements. So there's a list. Oh, let me actually clear that. So if we execute this piece of code, you'll see there is a list containing the numbers from 1 to 5. And so that's pretty standard. And now you've got a collection of items, and you can generate them from a function. For example, we saw range earlier, which generates a list of numbers. So for example, this one says generate numbers in the range from 2 to 12 with a step of 3. So in this case, it'll go 2, 5, 8, 11. And there you are. So there's just generates our list. But lists are not just about numbers. In fact, you can have any kind of Python data in a list, and of all different sorts. This is the thing we talked about, dynamic typing. Python doesn't really care about the types unless it has to. If it can ignore the type, it will. So for here, it says, I'm happy to just put anything in the list. So for example, here, my list contains an integer, contains a string, it contains a floating point number, and it even then contains another list within it. And all that's okay, no problem. So once you've got and created a collection called a list, you can do certain things with it. You can access the elements of the list using the square bracket and an index, like so. And then you can similarly use that to assign new values to things. So for example, we can change the value here of 3 to 4. One thing to note about Python, it's 0 indexed, which means that the first element in the list is mylist 0. So for example, we're looking at the third item in the list, so that's mylist 2 to access that. Some other languages, notably Fortran or MATLAB, are 1 index, which means the first element of the list is 1. That is not the case in Python, it's 0 indexed. And so there are, we've assigned our list, and now you can see the value of the list here is changed. And you can do other standard operations to your collection. You can add new elements. So we've added a 6 to the end, or you can move elements. Now it's gone again. Those are all kind of element-wise operations. But you can also do operations on whole lists. For example, you could join 2 lists together. So for example, I've had my existing list and I'm adding a new list to it. There you are. And there's some other kind of more niche functionality. For example, you can duplicate lists. So for example, if I take this list here, multiply it by 5, that means that I will create 5 copies of the elements in this list in another list, like so. So you got A, B, A, B, A, B, A, B, A, B, A, B, 5 times. And of course, what you often really want to do with a collection, like a list, is you want to do something with each of the items in the list. So we talked about the for loop. That's where repetition comes in. The sort of most elegant way to work on each item in a list is you say for each item in the list. So for my item in my list, do something with that item. For example, in this case, we're just printing it. But obviously that could be any much more sophisticated function that does some complicated data transformation or analysis. So that's a list. That's the sort of most basic data structure in Python. Another data structure that's very similar but slightly different is the tuple, which looks very similar. So whereas the list had square brackets, this is round brackets. It looks very similar, and you can access the elements in the same way. But what's different about a tuple, and this is important because it's used by Python, is that you can't change a tuple. Once you've created it, that's it. You can create a new one, but you can't change it. Oh, yeah, another spelling mistake. So this is called mutable versus immutable. So lists are mutable, you can change them. Tuples are immutable, you can't change them. So for example, if I tried now to reassign one of the values to a different value, then I will get an error called an exception. And you can see it says type error does not support item assignment. So I'm not allowed to do that with the tuple, where I am allowed to do that, as we saw over here with the list. So that's an important difference there. And this is useful in some areas where you need to pass something that can't be changed. You can pass a tuple. So that's the second. The third data structure that's part of standard Python is quite fundamental and provides a sort of next step in sophistication of data structures is a dictionary. So we're in a list, for example, here I've got a list of populations of countries. You just see the numbers and you access them via an index number. A dictionary is slightly more intuitive in that you have a key and a value stored together, which in data science is a bit more intuitive. It tells you a bit about what that data is. It's essentially metadata, as it's called. So for example, here I've got a dictionary of population data for countries in Europe. And so I have the name of the country with the population of that country. And so it becomes much more intuitive for handling and interacting with data. To do this way, the way you create a dictionary is instead of using the square brackets, you use these curly brackets. And then you have each of your keys, colon, value, key, colon, value, as many as you like. And so, for example, that looks like that. And instead of accessing with just numbers, you can access in a more intuitive way. So say, what's the population of France? You can access it that way. Similarly, you can reassign elements of your dictionary. So for example, if you now say population data France equals 70, you will change that value. You can see here now our dictionary says 70 in that position. And you can also add elements. So for example, if we try and access something that's not there, unsurprisingly, we'll get an error. Key error, Switzerland is not one of the keys in our dictionary. But we can, if the key is not there and you try to assign a value to it, it'll add that to the dictionary. So for example, we say Switzerland equals 8.55 million people. Our dictionary is being updated and it now includes Switzerland. And like a collection, like a list, you can also, this is the important part, is you can iterate through what's in the list and do something useful. If you just go say for something in dictionary, it'll give you the keys. So in this case, the country names, like so. A useful thing is what you actually want to do is iterate through the list of keys and values, so country names and populations here, and then do something with those. So if I do it that way, you can see it's getting the country name and the population from our dictionary and doing something with it. So in this case, I'm just printing it out, but I could be doing, again, something much more sophisticated and more data sciencey. So those are the core three data types in native Python, and we'll see how we use those to actually do data science, and hopefully generally moving towards things like a dictionary where you have the metadata, something telling you about the numbers, with the data itself. So at this point, I'd just like to introduce two types of data that we're going to talk about. This is particularly, there's probably other sorts of data, but in weather and climate, this is particularly useful. And there's a sort of difference to how you handle them. So one is tabular data. So this is a bit like the kind of data you might see in a spreadsheet or a database, where each row represents a data point. For example, in a payroll system, each row might be an employee. In a weather observation system, each row might represent a set of observations for a particular point in time. Each column then represents a feature of those observations. So in our employee payroll system, columns might be employee name, ID, department, salary, and so on. Or in our weather observation system, columns might be temperature, wind, time of observation, sunshine measurement, and so on. So that's tabular data. I'm going to look at that now. In a future notebook, we're going to look at gridded data, where rows and columns don't represent separate observations. The whole grid represents a single data point with many dimensions. So for example, in a weather forecast model, you might have latitude and longitude being two of the dimensions, but also height up through the atmosphere, time, or various other things. So you have a multi-dimensional array of data that represents a single data point. And we'll look at how you handle that in shortly. But first of all, let's just try and read some tabular data. Like I said, Python has lots of functionality right out the box, one of which is being able to read various standard data sorts, like, for example, a comma-separated value file or CSV file. So that looks like this, if you look at it raw. So it's just a series of rows of text with commas separating the values. And you can read that in using Python. So it has a library called CSV. And so over here, I'm saying open my file, which you can see over here. And then I'm reading that in using the CSV reader functionality. And then I'm going to, I can iterate through that because essentially it's got a list of rows in there, and I can do something with that. So if we execute this code, we'll see what comes out. It's printing out each of the values one after the other, and I can easily access the elements in that list. So for example, if I want to say, well, what was the temperature at 3 o'clock? I can say, well, this is the third row, so it's number 2, and the temperature is the second measurement, so that's 1, and it was 24. But now to demonstrate the virtues of dictionaries versus lists, in general for metadata, I can read the same file in again, but now read it into a dictionary rather than a list. And if I execute that code, we'll see once again, I'm opening my file, and then I'm using a different reader. So it's going now into a dictionary, and I'm storing it one after the other. Oh yes, in a dictionary, and we'll see what that looks like. So here's the dictionary, similar to what we had before, except now each value is in itself another dictionary. And the advantage of that, so for example, if I compare how I access a list, where I've got indices of 3 and 1, which don't necessarily mean anything to me. I've got to remember 3 was the 4 o'clock observation, 1 was the temperature column. Dictionary, I can say, give me the weather at 4 o'clock, and I want the temperature, and there it is, 20 degrees, as we see over there. And so this is how we're going to start thinking about using Python for data science, make it more intuitive, using metadata to think about the actual problem rather than kind of arbitrary indices and numbers. And so this is how you can access tabular data. And of course, now once you've got a dictionary, you can start iterating through your dictionary as we did here and perform operations like we saw in the first notebook. So that's the introduction to tabular data and Python data structures. Any questions at this stage before I move on to our next section on gridded data and maths? I'll take a drink of water in the meanwhile. Okay, pressing right along. So often we've kind of glossed over the sort of operations one might do on data at this stage, to show you can iterate through collections and do stuff. So when you actually want to start working around with data and performing calculations, an indispensable library is numpy, standing for numerical Python. But there's also some standard functionality that comes with Python. So there's a math module, random number generators, and various other things. So you can get started without numpy, but we'll see shortly. It's a very useful library. So what does math look like in Python? So we saw some of that. It's pretty simple. You can assign values and do calculations in the standard way. Let's clear that. So I've done some calculations, printed out the results, and so it's You can generate random numbers, and so on. So a useful tool for doing data science and performing operations, we said, is looping, repetition. But even more useful is a way of looping to create lists kind of in a nice compact way, which are called comprehensions, which is a feature of the Python language. So whereas before you saw we had, actually I should type that in here, we might have had a list that looks something like that. You can, that's a sort of quite a verbose way of creating a list. You can use a comprehension like this to do some quite interesting things in a very compact way. So you just have that same for loop and the operation, and it just creates a list straight away, for example, like that. And you can do the same thing with a dictionary, except instead of the square brackets like you generally have for a list, you have the curly brackets, and you have to specify a key and a value as a standard for a dictionary. And so, for example, you can say for the same for loop, generate a random number and assign the key to it, which is just the index in this case. And it looks like that. So those are quite useful in data science to compactly process each thing in a set of data, which could be millions or billions of elements, but with very little code. So that's one of the things that's quite nice about Python for data science. So in general, though, the core of data science is kind of two sorts of operations that you might want to perform. One sort of operation is where you want to do something to each item in a collection. And so you have the same number of output items as input items. So for example, here we're doing a very simple thing. In our list we've generated, we're going to times all the numbers by 2. And so we can use our comprehension construct to do that. So for each of the values in my list, perform this operation, and then we'll store it in a new list. And you can see there's the results over there. And you could do the same thing with the dictionary. Which is quite useful. There's also another way of doing it in Python, which is, it's not particularly important. You can get away without knowing it, but it's quite useful because it feeds into more complicated, real world ways of using Python, especially where you start using clusters of computers or cloud computing, is the map function. The map function is very simple conceptually. You say, do this function to each item in the list, much as we've been doing in our comprehension. So for example, if we defined a function called double, it's a very simple function. Obviously you could do a much more complicated function, but that would make our teaching complicated. You can then say, do double to each item on my random list. And oh, well, this is slightly interesting as a concept in Python as well. So unlike over here where you actually got a list out, here you've got an object called a map. We're not actually getting the result. And similarly, if I do that, and that's because Python is doing what's called lazy evaluation, which sounds like a bad thing. It sounds like a bad thing if your computer is lazy, but actually it's generally a good thing for your computer to be lazy. It's a bit like it's saying, okay, I'll do this when you need me to. And this is actually really, really useful for data science, because often what you want to do is set up some calculations, and each of the calculations might take hours to run. And you set it up, and then only when you actually need the results does it actually start, and then you can go away and do something else while the calculation happens. So there are many advantages to this that are perhaps not intuitive. So one of which is that one I've described, you set up your computer pipeline, so you don't have to run a command and wait 10 minutes, then run another command and wait 10 minutes. You can set up all the commands, then press go, and it starts the calculations, and then at the end you'll have your final results rather than have to keep coming back. So that's quite nice, but not particularly important. what's particularly important is the use case I mentioned previously of a sort of heterogeneous distributed computing environment. You can use things like the map function or other versions of that to send your very complicated data science calculation to a much bigger, more powerful computer or multiple computers and distribute your workload like that. So that's the power of this sorts of function. And you can also use it. There's a variety of tools that allow you to then be very clever about it. So break down your problem into smaller problems. If maybe your problem is too big to load the whole data set into memory, or to run it across multiple computers so you get your result faster. So this is another important feature of Python for the purposes of data science is the generator object, which is what you're getting here, for the purposes of lazy evaluation. Now, in this case, our example is tiny. We want to just get a result, so I can force it by saying, I want the result now, give me a list, by calling this list function. And instead of the map, I'll now get my list and my dictionary. Oh, that shouldn't be like that. Oh, yes. Sorry. And indeed, you don't have to have previously defined a function. Here I've used something called a lambda, which is a nice function. You can just define a temporary function on the go. I won't go into too much details. That's a whole nother way of programming. But for those who are familiar with the concept of lambda functions, I just thought I'd mention that Python can do that. Oh, time is getting on. The other sort of operation, so that's an operation where you have n items come in, n items go out. The other sort of operation you want to do is a reduction. You start with n items and you land up with like one item or some other less number, but traditionally essentially going from n to 1. So for example, you want to find, say, the maximum value in a list, or the sum of the values in a list, or the length of the list, or say the average of the values in a list. Those are all reductions. You starting with a large data set and you're condensing it down to something that helpfully gives you some more information and knowledge and understanding about what's contained in the data. So obviously here we're doing pretty simple stuff, but again, that can be any complicated calculation, and finding the mean and standard deviation of a set of data is a pretty standard way of starting to gain some understanding. So those are the two operations, and that's how you can easily do them with standard Python data. But this is kind of a very manual way of doing it. But generally, what we want to do is we want to start using higher level libraries to make that an easier, more intuitive process. And so I'm going to demonstrate that with gridded data that I talked about earlier, where each of your rows and columns is not separate data points, but all one measurement. And we're going to do that using the library called numpy, as I mentioned, or numerical Python. So we can use that to generate a whole grid of random numbers now. So you can see there you are, there's an array, I've got loads and loads of values in it. And so now, rather than if I want to perform an operation on each item, for example, I want to double it, I don't have to manually loop through all the items and do the calculation. I just say ×2 and the whole thing is now performing the operation on the whole object. So it's kind of abstracting away some of the details, which is the direction we want to be traveling in, away from manually handling each and every calculation to thinking at a higher level, a more abstract level. And you can similarly do other higher level calculations, adding two groups of values together. So that's our first sort of operation, or we can do a reduction as well. So for example, we can find the average of the two arrays added together, their thing, or we can do reductions on subsets. So for example, we might want to say, what is the average of each row in my data? And so here we've got, say, the same operation, mean, and I want to do it on axis 0, so that should be for each column. Yes, so that's finding the average of each column. So you can see we've got 5 columns, so we've got 5 results over there. Our average of each row. So we can see we've got 10 rows here, so we've got 10 results over there. And there's a whole range of very powerful calculations available through numerical Python that you can use. Just to briefly mention, for those of you who have a mathematical background, this is a representation called an array. There's also a representation called a matrix. So this represents a mathematical matrix and does mathematical operations on it. And just to briefly demonstrate how those two things are different, if I generate an array and a matrix, there are our values. If I multiply two arrays together, it does each element one at a time. So that element times that element times that element. Whereas if I do matrix multiplication, it does the proper mathematical matrix operation, which is to multiply this whole row by this whole column. So you can see the results over here. If I multiply my arrays, you can see the top left element there is the result of that calculation. Whereas if I calculate my two matrices, it's the result in the top left-hand corner is equivalent to that much more complicated calculation. So that's just a bit of background for those of you who have dealt with mathematical matrices before. This is quite useful in terms of the nitty-gritty of doing the details of data science calculations, but most of the time you won't have to deal with that because your higher level libraries will take care of that. So this is an example of gridded data. So, for example, we can load, again, using numpy. One of its uses is to handle data and load data from files. So, for example, I've saved an array of temperature data in this file over here. And I can load it, and you can see I've loaded it into an array. But just to preview our next session, you can see here, we don't actually know much about what these numbers represent. We don't know, I've said it's temperature, but you don't actually know that otherwise. What units it's in? You might guess it's probably in Celsius based on the range of values, but it might not be. It could be somewhere really cold. It could be Canada, and this could be Fahrenheit. Or we might also say, again, what area these temperatures come from. We don't know. So this is what we're going to be talking about in data models, how we combine, like we have the keys and the values in the dictionary, how we combine metadata more fully to do more sophisticated data science operations. And that will be the focus of our next session. But that's all on gridded data and maths for the moment. We'll move on to plotting in a moment. Any questions? There's a question from Landry. What's the difference between numpy and the previous one we saw? I don't know if you want to just expand on that question a bit, Landry. It's which previous one are you referring to? Yes. So the importing of data. So those were importing different sorts. So if you go back to here, so here we were importing data using the CSV library. So this is a standard Python library for reading from CSV files, which, as I said over here, it's a sort of spreadsheet type format. Here we're using NumPy to read in data. This is in a binary format, and it's so it's not a CSV file, it's a different data format. And although it's also two-dimensional, like a CSV file, it doesn't have to be. It could have been a 3 or 4 or 5-dimensional array that can be handled. So it's got that additional functionality. So like I mentioned, in weather or climate data, we often have dimensions for latitude, for longitude, for height in the atmosphere, for time as you go through our through the simulation, as well as often we run multiple quite similar simulations with slight random changes to model uncertainty, and so that's another dimension. So that's the difference between those two import methods. Hopefully that answers your question. Basically, they're different import methods for you importing different sorts of data. Yes, the numpy format, that's something that's native to numpy. It's just a binary format, so you have to write out and read in using numpy. But it's become fairly standard, but it's a very low-level format. So we'll see in our next session, we'll be looking at more higher-level data formats. So we'll be looking at netcdf files for gridded data, which is a standard way in weather and climate. But CSV files at more sophisticated ways to read and create those using other libraries. But you can also write out your files in numpy in a plain text format, just in a text file, so you can see it, but it tends to be much larger files if you use the text format. I see we're up to 3 o'clock, so I'll just move quickly on to our last thing about plotting, in case people need to go. So one of the last standard thing you want to do probably is in data science is to visualize your data. Humans are very good at taking in information visually. So if you can create a nice intuitive graph based on your data, then it's a very good way to present the information to your customers or your users or your colleagues. And so Python has some libraries, I should say, which do a very good job of creating plots very easily. And so the most standard way is matplotlib. There's various libraries that build on top of that and provide more sophisticated functionality. But as a starting point, matplotlib is quite simple to use and get started with, and frankly meets most of one's needs most of the time. So you can find some links to more information about all the things you can do, and the gallery is particularly nice. It just shows you some plots created with matplotlib, and you can quickly see how sophisticated the plots you can use. But scientists all over the world routinely use matplotlib to create the plots for their papers and reports. So you can see we use the import function, which I haven't actually mentioned in Python, but that's how you bring in libraries. You might have seen that in the last one, I didn't mention it. That's how you bring in third-party libraries, as well as the native Python libraries that aren't loaded by default. Because it would take a really long time to load all the aspects of Python, some of them you have to manually load. So in this case, this is a third-party library, but you also saw CSV. CSV is a part of standard Python, but it's not loaded when you load up Python, as I showed you earlier. So you have to specifically import it. So here, I'm going to import matplotlib and numpy so I can use them. And then just show you some three basic plot types. So the first one is a basic line plot. So showing a value varying usually over time. It could be over something else, but usually a value varying over time where there's some sort of smoothness to the way it varies. It doesn't just kind of randomly jump around. So for example, you might have a stock price varying over a day, or the temperature varying over a day. Or maybe you're monitoring your factory output as the quantity of some or other good produced in kilograms. So for example, if we generate some random data and plot it, here is a nice graph of our data. So I didn't show you, this is what our data looks like that we're plotting. As two lists, so two arrays, one-dimensional arrays. And then obviously it's much more intuitive to see what's going on when you look at it visually in a graph. So that's your standard line plot, and you can see how we did that quite easily, just using matplotlib.pyplot.plot x data and y data. You can though do more than one line on your graph. So this is an axis, and you can do multiple lines within the axis. So for example, here I've got 3 sets of data that I'm comparing, and you can easily have control over the color, and you can do dots instead of a line, and so on. So you can easily differentiate and compare different forms of data, which is a core part of what you're going to be doing. Any kind of data analysis is looking at different data sets and comparing them. So that's type 1. Part 2 sort of of your standard plots is a scatter plot, where there isn't a kind of smoothness to data varying, say, over time. You've just got individual data points that are kind of not connected or ordered in any way. So, for example, you might be plotting, say, the height versus weight of people, or plotting house size and house price together, or plotting temperature and rainfall at different locations. And so I've generated some more data. So in this case, I've created some randomly generated heights and weights, and there you are. So there's our scatter plot. So you've got different points shown on a graph. And I've randomly colored some of them in green, some of them in red. That's no significance, just to show that you could color them differently. So for example, that could have been, I should have done something more meaningful with that. But it could be from data from 2 different sets of something. In this case, you can see they're more or less interchangeable. But you could, if they were kind of, if all the green was over here and all the red was over here, that would tell you something about your data. The third and final type is a bar plot. So typically where you've got kind of quantity of different things that don't really have an order or kind of connection between them, just different observations or measurements. Another common plot, I'm sure you've seen in Excel and newspapers and so on, is a bar plot. So you might be plotting house prices, average house prices in different neighborhoods, or the number of employees at different companies, or say the average temperature in different cities. So there's no kind of order or connection, just a set of measurements. And again, you can just use a simple interface, bar, and then a list of values. And so you can see here, we've got different values of, say, temperature in regions. So that's about 18 degrees, 21 degrees, and so on for different regions, not connected. So those are the 3 basic plots you can do very easily. But you can also start to build on that and do things together. Like I said, you often want to compare things side by side. So you might want to have multiple plots side by side. And so in matplotlib, there's the idea of figures and axes. And so the interface that we've been using so far, matplotlib.pyplot, is sort of frowned upon. The more sophisticated way to do is explicitly create a figure using this function here, figure, and then add an axis. So an axis is this sort of Cartesian axis here. And you can have multiple of them in a figure. And the reason you might want to do that is because then you can save that out as an image and use it in your report that you're writing, or share it with colleagues. So for example, here we're going to put all 3 of our plots together in a single figure so we can compare them nice and easily. So you can see I've created a figure, then use this thing called add subplot, which is adding axes within my figure. So this means I want 1 row of axes, 3 columns, access the first one, access the second one, access the third one. And so for the first axis, I add a line plot, second axis, I add a scatter plot, third axis, I add a bar plot. And so you can see there are our examples side by side. And so if you might be able to compare different sets of data very easily. And so those are the kind of core things you might want to do. But just to mention, you can also do more sophisticated things. Will be particularly with gridded data. For example, if you had a field of temperatures, you might want to see like a sort of map of that. And so we have 2D plotting formats. For example, this is a filled contour plot, which we'll talk about more in the next session when we look at some real world weather data. And so you could be plotting a 2D field like that, or indeed the same thing in a 3D plot as well. So I won't go into more of that. You can look at that in your leisure in more detail through the links provided on this notebook, which we'll distribute after the session.
Brilliant. Thank you very much, Stephen.
See, there's some questions.
Yeah.
Since this is interactive, you run a block of code. How do you know which plot or image corresponds to data? So I guess so for example, let's take a look at this one over here. So here is the results of executing this block of code. So you kind of have to look at then what's in the code to see which data is being executed, but also hopefully you see I've gotten a title to my plot, so hopefully the description of your plot should tell you all you need to know about what data is there, and hopefully the names of your variables containing your data will correspond to what you show in your plot. But also here you can actually just see what code is being used to produce the plot right alongside the plot, and so you can kind of figure it out that way if you want to, or hopefully through the naming of variables, however you want to do it. In general, you should also have some text explaining what's in the plot as well. That's kind of the virtue of Jupyter notebooks. So hopefully that way you can figure out which plot corresponds with which data from the description that the person is given, as well as the code. Oh, an interesting question here. Matplotlib is better than MATLAB. Well, better, I don't know about that. I would say yes, I preferably use it. So obviously one of the virtues is Matplotlib is open source and freely available, whereas MATLAB is not free. But also there's probably a much more active community now around the Python ecosystem compared to MATLAB, because it's freely available. And so that user community is, and the range of tutorials and references and example code that's available is the real strength. Basically, whatever you're thinking of doing in Matplotlib, someone's probably done it before and they've written a blog post and they've got some example code available for you to use. So it's very easy for you to get started, or even very quickly be doing some pretty advanced things just by following the material that's available online. Any other questions on what we've done before? Feel free to ask any further questions via email or at the next session, which is in 2 weeks' time. As I said, we'll be distributing the link to these notebooks shortly.
Brilliant. Thank you very much for that, Stephen. And like I said at the start, we'll be sending through all the links through everything, and I'll also include the link to the next session so that you can sign up to that as well if you haven't already. Brilliant. Thank you very much, everyone. Enjoy the rest of your day and hopefully see you back here again in 2 weeks' time.
Super. Thank you very much.